Remember in derivatives that we talked about the idea of a gradient, and the gradient basically represented this slope or the rate of change at a specific point if we were to find the magnitude of that. If we were to find the magnitude, it actually found the fastest rate of change at a specific point. So how can we apply that to vector calculus? So a gradient field is going to be we're going to take the derivative of the function fxy, and that's going to produce the slopes if we multiply that by I and j at the specific points on that vector field. So we're going to be finding this gradient vector field, and we're going to take a look at what it does and specifically what it looks like. So let's consider a basic function, a really easy one, f of xy equals x squared plus y squared. We know that this is going to be an elliptic paraboloid in 3 dimensions. We've seen that many times. So if we were to just graph it really quickly, this is what we get. Okay, just a basic elliptic paraboloid in 3 dimensions. So the easiest part of the problem, find the gradient vector field for f. We're going to plot the level curves. So this goes back a little ways to be able to define level curves and plot them. We're going to plot specific gradient vectors on the same graph. And then finally, we're going to make some sort of deduction about what it means. So letter A, the easiest part, okay, we're going to find del f. All right. Now del f is going to be a vector field. So del f xy. Now the derivative of the function with respect to x is 2x, and we're going to multiply it now by I. Derivative of that function with respect to y is going to be 2yj. Right? So that's about as easy as it gets. For the level curves of the function, well, all we're going to do is we're going to replace fxy with k. So remember, level curves, you just replace it with a constant k. So k is going to be x squared plus y squared. We're not finding level curves of the gradient vector field. We're finding the level curves of the original function. And so we get, if I think I specifically said plot the level curves when k is 1, 4, and 9. So we would say 1 is equal to x squared plus y squared. We would say that 4 equals x squared plus y squared. And 9 is equal to x squared plus y squared. And what we can say very easily is that the level curves are going to be circles of radius 1, 2, and 3 respectively. Now remember, a level curve is a 2-dimensional plot on an xy plane. Okay, so these are circles of radii 1, 2, and 3. And if we were to plot those, and I'm going to plot those on the next page, I'll plot them right here. That should be enough room. As best as we can. So we're going to have a circle of radius 1, a circle of radius 2, and then finally we'll have a circle of radius 3. Okay, so now I'm not going to label these, but we will see in a little bit what they mean with respect to the gradient vector. So next part of the problem, we are going to plot these vector functions. Okay, so these vector fields. I'm just going to cut and paste them down here because we need to first of all evaluate them. All right, so we're going to find and plot. So the first one that we have, del f at 1, 0. This one's pretty easy. So del f at the point 1, 0. And remember, our function del f was 2xi plus 2yj. Well, that's just going to be equal to 2 times 1i plus 2 times 0j. Or in other words, just 2i. All right, so if we go back up, and I'm going to plot these in red so that way we can see what these functions are. So the first function that we have is just 2i at the point 1, 0. So recall we were able to do that. So here's the point, 1, 0. And that's just going to be 2i, which means that it's going to go to the right 2 units. It's actually going to terminate at the point on the circle of radius 3, which is just coincidental. Right. Another one we have is del f at 0, 3. All right, so that's going to be 2 times 0i plus 2 times 3j, or that's just going to be 6j. So we're going to go to the point 0, 3, and just imagine that we're going to have a vector of magnitude or length 6, and so that vector is just going to shoot directly up, and it's going to look something like that. Okay, so that's going to be the vector 6j. This could be the vector 2i. All right. So those are pretty easy. All right, and some of us might start to see a pattern, but if not, don't worry. We'll see a pattern as to what's going on in a moment. Let me make that look like a 2. So a third example. Now this time we're going to have 2 inputs. So we're going to have root 2, root 2. So DelF at root 2, root 2. One second, it's pausing. All right, so DelF at root 2, root 2. And this is pretty easy to see. That's going to be 2 roots of 2i plus 2 roots of 2j. Now if we were to approximate 2 root of 2, which might not be a bad idea, 2 roots of 2 is 2.83 approximately. So I'll just put this in parentheses, that this is going to be, or we could just do it in the hard brackets, 2.83, 2.83. And so we would go to the point 2 roots of 2, or I'm sorry, root 2, root 2. Now the point root 2, root 2 is the point 707, 707. Right? And we're going to go to that point. So root 2, root 2. Oh, I'm sorry, that's root 2 over 2. So that's not right, sorry. So square root of 2, I think, is 1.41. Yep, 1.41, 1.41. That's going to be the point 1.41, 1.41. And then this just tells us how far we're going to move in each direction. So we're basically going to move about 3 to the right and 3 up from the point 1.41. So 1.41, 1.41 is about 1.5, 1.5. That's about right here. And we're going to move 3 to the right and then 3 up, approximately. Okay, so we're going to get a vector that probably looks something like this. Okay, so this should be 2 roots of 2i plus 2 roots of 2j. All right. And then finally, the last vector that we have is 1, 2 roots of 2. All right, so DelF at 1, 2 roots of 2, that's going to be pretty easy. That's just going to be 2i plus 4 roots of 2j. All right. And we already know what 2 roots of 2 is, so the point that we're going to is 1, comma 2.83. Right? And then from there, we're going to have a vector that goes 2 to the right, and then 4 roots of 2 is going to be 5.66 approximately. So we're going to have a pretty steep curve that time. All right, so we go to the point 1 comma 2.83. So that's probably right about here. Okay, so it's just a little bit less than 3, which would be the highest point on that third circle. And then we know we're going to get a really steep ascent. So it's probably going to look approximately like this. Okay, so that's going to be our 2i plus 4 roots of 2j. All right. So hopefully it's easy to understand how to plot those. Now the last part of the problem is, what deduction can you make about the relationship between the gradient vector as well as the level curves? And what you may have noticed already is that every time that we construct one of these gradient vectors, it looks like that not only is it tangent to the point, or I'm sorry, it's not tangent to the point, it's actually going to be perpendicular to the point, or orthogonal to the point. Remember, we talked about the idea of orthogonal earlier in the course. So, and that's true for every single vector that's a result of the gradient vector field, is that we always get a perpendicular or orthogonal. Okay, so what we can say for part D is we can say that the vectors of the gradient vector field are orthogonal to the level curves of the original function. All right. And I guess we should say orthogonal to a level curve of the original function. And we're not necessarily sure which one it is, but it's going to be a point on a specific level curve. All right, so that's the relationship of the gradient vector field. So obviously it's not too difficult to be able to find these and compute them, but it is important to know that there is that relationship of perpendicularity that occurs as a result of this.